My name is Cong from University of Waterloo. Today, I'm going to show you our latest work on the compilation of lexical effect handlers. In particular, I will show you a novel compilation technique that makes lexical effect handlers zero overhead. You will see what I mean shortly. First, some background for our work. Effect handler is a powerful language feature that allows programmers to write programs with interesting control flows. It subsumes many popular language constructs like async await, coroutine, and generators. Effect handler, though powerful, suffer from a modularity problem. Here's an example. Assuming you are an application developer, you import a plugin and a framework from third-party libraries, and you invoke framework by instantiating the plugin. Now, say you want to monitor the usage of plugin by the framework. You create a wrapper function that calls plugin and raise the login effect. And you also install a login handler in your application. Programmers expect this to work because both the raise side and handle with expression use the same name login. They would expect them to refer to the same thing. However, many works on effect handlers use a semantics based on dynamic scoping. When an effect is raised, it is handled by the closest enclosing handler on the stack. To see how such semantics could go wrong, let's assume that the framework that you imported install a handler for its own purpose. Of course, as the application developer, you do not know that. If you run this program, the login effect raised from plugin will be accidentally handled by the handler in the framework. This behavior makes it very difficult to reason about the program. For example, if you import a framework that does not install an enclosing login handler, then your application will work as expected. We know that this problem is similar to the modularity problem with dynamically scoped variables, which have fallen out of favor since the 80s. Recent work has proposed lexical effect handlers as a promising alternative. In a language with lexical handlers, the handle with expression introduces a variable binding. When a lexical effect handler is installed, the runtime generates a fresh name for this handler. This name substitutes for the variable inside the handled body, and it is passed down the call stack, eventually reaching the call site. Besides, names are values that can be captured by the closures. Because the raise site is precise about which handler it raised to, the problem of accidental handling is avoided. Here's another presentation for the same expression, which highlights the stack structure. The program has two stack frames, a handler frame at the top with name 314, followed by the current redux. This slide compares the handler with lexical and traditional semantics. We can see that with lexical semantics, every handler is given a globally unique name when it is installed. The traditional semantics does not have such guarantees. Prior work have also shown formally that programs built with lexical effect handlers enjoy modularity. However, when compared to the traditional handler semantics, the lexical handler semantics has a performance disadvantage in that every function needs to explicitly receive handler arguments. The passing and receiving of the extra arguments impose a runtime cost, even for rarely raised effect, such as exceptions. And we are concerned that even though lexical handlers has nice theoretical properties, language designers might still shy away from them because of this overhead. Generations of language designers have advocated for zero overhead principle for exception handlers. This idea is best described by the quote from Jung: "What you don't use, you don't pay for." Zero Lexa is our attempt at achieving this goal, making Lexa the first language to have zero overhead lexical effect handlers. In the next few slides, I will demonstrate the technique by walking over two examples. We will first see a non-zero overhead execution, which is the state of the world now, and then we will figure out how to make the execution zero overhead. Here's the first example. I show the program on the left and a stack diagram on the right. Please only pay attention to the diagram on the right. Now, as the program runs, function main install a handler, which is given the address 5. This address acts as the name of the handler and will be passed down the stack. This address, okay, now the next, the main calls foo by instantiating foo's handler parameter with this handler. The black box here denotes a handler parameter binder, and the arrow denotes the parameter instantiation. Inside the function foo, it installs another handler, which is given address 6. It then calls bar by instantiating the two handler parameters. Finally, bar raises to handler at address 5, which transfers the control to the stack address 5. Similar things happens when bar raises to handler at address 6. Now let's ask ourselves, can we locate the intended handler without passing down addresses? The key observation is that handler provenances, which are represented by the arrows, are known statically. Even if we don't explicitly pass down the addresses, we still have a way to know where the handler passing originates. We can just trace back the static provenance information and find the intended handler. Let's see in action how handlers are located in 0 Lexa. When an effect is raised, the control goes to a runtime stack worker. The stack worker carries a state called clue. It is a single integer denoting the de Bruijn index of the handler variable responsible for the raised effect. In this example, the clue is initialized to 0, which is the de Bruijn index of handler parameter h2. The stack worker walks up the stack. At each call site, it transitions the clue according to how the parameter is instantiated. In this case, h2 was instantiated by a local handler inside foo. Since this local handler's de Bruijn index is 0, the clue is updated to 0. Finally, while inside the foo, the stack worker finds a local handler with de Bruijn index 0. It thus successfully finds the handler. 0 Lexa also works with higher-order functions, which I'll demonstrate using a second example. Some of you might get lost in the next 2 minutes, or you might already get lost. But don't worry. The takeaway here is that the arrows on the diagrams are known statically, and the stack worker is simply following these arrows. Similar to the first example, this example has 3 functions, main, foo, and bar. Notice that bar is a first-class function that is defined inside the scope of 2 handlers. Also notice that foo is a higher-order function that takes in effect parameter alpha and a term parameter g, where alpha stands for the effect that g raises. At the call set of foo, the effect parameter is instantiated with log and exception, representing the handlers that the term argument can raise to. Now, assuming that we are at a point on the right, main calls foo, foo calls bar, and bar is about to raise to handler log. We start stack working with an initial clue infinity. We use infinity to denote handler variables bound outside the scope of the immediately enclosing function. And in this case, log is bound outside the function bar. From another perspective, log is captured by the function bar. Furthermore, the clue contains an extra field to record the effect name. This information will be used to disambiguate a fork on the provenance path, which you can already see on the diagram. When a stack worker arrives at the call site of bar, it attributes the effect to alpha, which represents the set of handlers captured by bar. Since alpha's de Bruijn index is 0, the clue is transitioned to 0. Next, the stack worker reaches the next call site. The clue attributes the effect to alpha, but alpha is instantiated with 2 handler variables, one for handling exception and one for handling logging. The second field of clue now plays a role in disambiguating this fork. Because the variable log has a matching effect name logging, this variable is chosen. And the clue is updated to carry the de Bruijn index of log, which is 0. Finally, the stack worker finds the local handler with de Bruijn index 0 inside main, and with that, we've successfully located the target handler. Now let's see what the compiler does to realize the stack working and clue transition. The first stage of compilation involves compiling a source language with handler passing into a target language without handler passing. But each call site is now annotated with a metadata. This metadata, encoded in de Bruijn indexes, records how the handler parameters would have been instantiated. In other words, the call set metadata keep track of the handler provenances. Next, the target language, now without any handler passing, is further compiled to binary as is shown. And the call set metadata that record handler provenances are compiled to a static lookup table in a data segment in the binary. They can be efficiently looked up using the return address of the function call. Notice that zero Lexa doesn't instrument extra code in the binary. The stack worker only consults the metadata when an effect is raised, so the cost is entirely off the mainline execution path. Furthermore, we prove that the translation from the source to target language is semantic preserving using a simulation argument shown. This result implies that the handler found by the stack worker is exactly the handler that would have been used if the handler was passed down explicitly. We integrate zero overhead technique into the existing Lexa compiler. Programmers can write Lexa code and declare some effect to be exceptional. The Lexa will compile exceptional effect handlers using zero overhead technique, while compiling other handlers using handler passing. Now, for the first part of evaluation, we ask whether zero overhead implementation is really useful. We hypothesize that exceptional handlers that are rarely used would benefit from the zero overhead implementation. We carry out a simple case study where coroutines cooperatively yield control to each other. On the graph, the x-axis denotes how often yield happens, and the y-axis is the time to finish the tasks. The larger the x-axis, the less frequent coroutine yield to each other. The graph indicates that when the x-axis is small, which means that yield happens frequently, the performance of zero overhead technique is bad due to the cost of frequent stack working. However, as x-axis moves to right, yield happens infrequently, and zero overhead starts to have a performance advantage. We compare the performance of zero overhead technique with handler passing using benchmarks that use effect infrequently. These programs mostly use exception handlers to defend against unusual conditions, which actually never happen during the execution. Because the zero overhead compilation avoids overhead of handler passing, we see a clear performance gain for these programs. In conclusion, we hope that lexical effect handlers, now armed with this zero overhead technology, would appear more appealing to future language designers. Thank you for your attention.
Very nice talk. So the cost that you remove is the costs of me having to pass down explicitly the parameters, right? It's not the runtime cost.
It is runtime cost because with lexical effect handlers, you need to pass down the handlers. You need to pass down names, for the function to raise to that to the handler. So you need to pay some cost at the runtime.
But if I pass a parameter, couldn't the compiler figure out that I just pass a function address?
Sorry, say it again?
If I pass a parameter, then how is it different than just the compiler figuring out that I need to pass a function pointer? Yeah,
you mean the compiler could figure it out sometimes, but say that you are using separate compilation or you're doing modular development, right? In this case, the compiler don't have global knowledge to do this kind of optimization, so it has to be passed down explicitly.
Okay, thank you.
Thank you.
Hey, cool work. So you have these two different implementations, right?
Yes.
The one that seems to work really well for if you use effects a lot, and the other one when you use them rarely. Do you also incorporate, or maybe already, like caching the information so that only the first time you use the stack worker, then cache the address so you can just switch to the faster one?
That's a very good point. I see what you...
Because then you only pay once, right?
Right. We did not implement that, but I can see it working, yes. Yeah. That's a very good point.
Okay.
Thank you.
Hi, thanks for the talk. Could you go back to the second example?
Okay.
Thanks. So what happens if we just have let bar in bar, then we return the function that captures the effects? How do you prevent them from escaping the lexical boundary?
Sorry, can you repeat that?
What if we have the program let bar in bar? So
let bar in bar.
Yeah.
Okay.
Yeah. Then we are returning the function that closes over log and the exception effect.
Oh, that's a good question. Basically, the source language have a type system that will prevent any function that captures handlers to escape the scope of handlers.
So you're keeping track of the captures?
Yes, yes.
Okay.
So something where I did not present here is that we have a type system that helps this compilation.
Okay.
So yeah,
Thank
this
you.
such type system will prevent this from happening.
Okay, thank you.
Thank you.
Okay, so let's thank the speaker.